Greetings and welcome, friends. Today we are talking about trigonometric functions on the unit circle. Now, unit is typically referring to the number 1. All right, so let's first draw what the unit circle is. It's going to be a circle of radius 1, is what I mean by unit circle. Let me draw a really good picture here, I hope. That'll explain everything. I might even make this a large-ish picture. All right, so here's my coordinate plane, and I'm going to take my unit circle and throw it smack dab onto having a center of the origin. Actually, what's crazy is you guys are so good with conic sections, you would even know that the equation of this circle is x squared plus y squared equals 1. Craziness. All right, so imagine here's 1, here's 1, here's -1, here's -1, right, like that. So my unit circle would look something like this. And it's going to be kind of sad, lumpy, gross circle. But it looks something like that. All right, and now this is the thought process that we're going to take. Imagine a point on this unit circle. Okay, so here's a point on my unit circle somewhere. Let's draw one in the first quadrant somewhere, right? So something like that, that, or that, right? Maybe I'll try to draw it so it's not exactly at 45 degrees. Doesn't matter though. So the coordinates of that point I will refer to as x, comma, y. That makes sense. And let's see, what is, just a question, what are the possible values of x on this unit circle if this point was anywhere on the circle? What's the biggest number x could have been?
1.
Right, x could have gone as far right as 1. And what's the smallest it could have been? -1, right? It's at smallest -1. So x is just going to be bouncing back and forth between these two, ding, 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 like that, right? And the largest value for y would have been, right, +1 up here, and the smallest would have been -1 down there, and y is just going to be bouncing back and forth, you know, so like here it's somewhere less than 1, but it's definitely positive. I don't know, it's probably as high as like 0.8 something, or 9-ish, who knows. So, now, how far is this point from the origin? What was that? 1 unit. How do we know? Yeah, because I said this is a circle of radius 1, and definition of a circle is it's a set of all points, locus of all points that are equidistant from the center. And if the radius is 1, then that means it's 1 unit to any point on the circle, right? Now imagine this. Imagine I was to, from this point, drop a vertical down to the x-axis. Bam! What angle would that make with the x-axis? A 90-degree angle. And imagine this dimension here from the origin over to where that point was, like so. And it appears as though I have a triangle that you might describe as a right triangle, right? Now, question, what would the length of this leg of the triangle be? Oh, half? Well, I mean, it's possible, but not guaranteed. I mean, I don't have any numbers on it right now, but I do have a value that it would represent, and it's actually x units across, right, over x units here. And what is the other leg here going to be equal to? It's actually going to be, yeah, it's y units high. This point was y units above, so it's actually going to be y units there. So it turns out with this sort of method or technique, I can really interrelate circles and right triangles. There's actually a lot of other relationships between circles and right triangles, but we're specifically going to look at this. And if I want to also combine my other concept from 2 sections ago regarding angles in standard position, this angle right here I could refer to as theta, right? So my question for you is this. What are the values of sine and cosine on this unit circle, specifically of theta? So for instance, sine of theta would equal, well, let's see, sine is the opposite to the hypotenuse, so the opposite is the y, the hypotenuse is the 1. So sine of theta is going to just equal y over 1, right? Which is just y. And what is the value of cosine of theta? Right, adjacent to hypotenuse, so that's x over 1 or just plain old x. So sine theta is y, cosine theta is x. What I want to point out here is that another way I could represent this point, I could have thought of this point as just cosine theta comma sine theta, right? So peculiar indeed. So it turns out that both cosine theta equals x and sine theta equals y, both of those happen to be functions of theta, and they're often referred to as circular functions. All right, because if I take sine of whatever this angle is and I'm moving around the circle, I'll get different values, and it happens to be one output for every input. So it's a function, right? And it's on a circle. So circular functions, hooray! Friends, yes. So, well, let's just keep exploring here. What would the value of tan theta be for this situation? Right, tan theta would be the opposite to the adjacent, so that would be y over x. And we actually just saw that on a homework problem a moment ago, if you recall, when we were talking about slope, right? That I said tangent theta is equal to rise over run, y over x, which is equal to slope. Which if you wanted to ask what is the slope of this line, it is up y over x, which is also tan of theta, interestingly enough. All right, so there's my original classic 3. I could then also ask the question, what is cosecant theta? And that's just going to be the reciprocal of this, or 1 over y, right? The reciprocal functions are always nice and easy to get. Secant theta, I'm writing these in somewhat of a weird order, perhaps. Secant theta is the reciprocal of cosine, so that'd be 1 over x. And I could also find cotangent theta, which is the reciprocal of tangent, so that's x over y. Wonderful, friends. Isn't it wonderful? So, using these concepts, let me ask you this question. Here's a little example for us. What is the value of cosine of 180 degrees? Well, no, we don't actually. Now, what did I say earlier? I said cosine is equal to x. Okay? So cosine is equal to x. So let's draw a picture of this 180-degree angle. The initial side would have been the positive x-axis, right? And a 180-degree angle, what would that look like? Let's see, here's 90 degrees. It'd be over there, right? And what would the coordinates of this point be if this was a unit circle? No. Negative. Well, if it's a unit circle, it's 1 unit away, so -1 and comma 0. Well, actually, that's a good question. We'll talk about that later on in this lesson. But we're going to use the unit circle to find the value of cosine 180. But since cosine is a ratio of opposite to hypotenuse, it turns out no matter what size I scale up or down that circle, the ratio of its opposite, sorry, I said opposite, didn't I? The ratio of its adjacent to hypotenuse, no matter what radius it is, the ratio is always going to be the same. So using the unit circle can be a nice way to just simplify it for starters. So what would cosine of 180 degrees be? Cosine of 180 would be -1. How did you know that? Right? Cosine is just going to be the x. Right? So it's just whatever x happens to be for that angle, oddly enough. So I could actually even ask a follow-up question. What is sine of 180 degrees?
0.
And how do you know that? Because sine is y. So I just was able to calculate, right, sine of 180 degrees. Now, one thing I want to point out, so far our values of sine and cosine and tangent, they've always been positive, right? Because we only so far have used them in right triangles, right? And the sides of right triangles are always positive, and a positive divided by a positive, if I'm finding a ratio, is positive. So this is kind of interesting. We've actually just found our first negative value here, oddly enough. Peculiar, peculiar indeed. And we're going to be able to use this sort of concept to find the values of sine and cosine. Well, let me ask you this question. Let's actually consider this for a moment. If cosine is always x and sine is always y, let's consider the quadrants here for a minute. I'll call this the sines of cosine and sine. Or I could say the sines of cosine and sines, and then it's almost palindromatic there, but it isn't. So if I want to specifically talk about the sines of cosine and sine, let's think about, for cosine theta, sine theta, let's think about the quadrants. All right. And in the first quadrant, all right, so here's quadrant 1, 2, 3, and 4. 1, 2, 3, and 4. So in the first quadrant, quadrant 1, cosine, remember, is equal to x, right? Sine is equal to y. What sines are all of the x values in this quadrant? So if I plot a point here, what would the x coordinate be, positive or negative? Right? It'd be to the right of the origin, so these would all have positive x values, right? So cosine has a positive outcome if our angle happens to land in quadrant 1. What about quadrant 2? Well, that's to the left of the x-axis. Actually, these little arrows might be helpful. So cosine is going to be negative in that quadrant. Quadrant 3, negative because it's to the left. And quadrant 4 is positive. So cosine happens to be positive or negative in those quadrants depending on where the terminal side of our angle falls. Now, we just did a problem where we didn't land in a quadrant. We had a quadrantal angle, right, where it landed exactly on the grid. And in those cases, you can actually just take the sine of the point that happens to be on that axis. But I would also like to point out that if I had a point land on this axis, it's between two negatives. So it's actually going to be negative, right? Whereas if I had it land exactly on this axis, maybe we'll ask that question in a second. What's cosine of 90 degrees? What's between a positive and a negative? Yeah, it's actually going to be 0. But I won't get into, I don't want to complicate my chart too much, but I just want to point out the quadrantal ones you can kind of figure out based off of these signs as well a little bit. Let's figure out sine. In the first quadrant, the y values are above the, right? I would have moved above the origin, so they would have been positive. Second quadrant, sine is positive. Third quadrant, negative because I'm going below the origin. And fourth quadrant, negative. All right, so I'm going to use this concept of where that point lands to determine the polarity or the SIGN sign of my sine or cosine ratio. Okay, so kind of interesting so far. So let's do an example with this. Exemple. Let's find the value of, let's say, cosine of 135 degrees. Let me show you how I'll do this. So I'm going to draw a picture of this. So I'd have the initial side over here. And what quadrant is 135 degrees going to land in? Yeah, that's the second quadrant. It's actually going to land right here-ish. And 135 degrees looks like that. So, now, I don't know the cosine of 135 degrees. In fact, I don't have it memorized. But let's find the reference angle of this. You guys remember how to find the reference angle? Let's see. So here's theta. The reference angle is alpha. You guys remember the definition of a reference angle? It's the acute angle between the terminal side and the x-axis. So in this particular quadrant, how could I find alpha? Yeah, so alpha is going to equal 180 minus theta, right? And that's specifically the reference angle in a quadrant 2. This is my own notation I'm coming up with, but that's a specific little formula only for that quadrant. Or you could just kind of look at it and be like, oh, 180 degrees minus my theta is going to equal the leftover. Angle addition postulate really is all it is. So 180 minus 35, what's alpha equal to? .45 degrees. So I'm going to say that cosine of 135 degrees, all right, is equal. Now, if 45 degrees and 135 degrees, all right, land in the same spot depending on how I'm looking at this, all right, I'm going to use the reference angle for 1. So I'm going to rewrite this as cosine of 45 degrees. But in order to use this reference angle, I have to also determine what sign cosine is going to be. In the second quadrant, cosine is negative. So cosine of 135 is going to equal the negative cosine of a 45-degree angle. All right, and part of the way you could explain that is I could actually, if I wanted, I could draw this little right triangle, and here's my angle that's 45 degrees, and this is actually a negative x value, and my radius would still be 1 or whatever, and the ratio would be a negative x over a positive 1. But don't worry about all that. All you need to know is that you can break an angle down if you know the sine of the quadrant that it's in for that function, and if you know its reference angle. All right? So maybe I'll actually write a little note. Sine of cosine in quad 1, or sorry, 2. And the 45 is the reference angle. So what is cosine of 45 degrees? Did we have it memorized? It's negative something. Root 2 over 2. Precisely. And actually, to verify this, let me see if my calculator will show up here. Ah, it's got the blurries. Here, let's have it focus here. Enhance. Zoom in. Oh, really? You call that focused? Come on, calculator, camera thing. Alright, this apparently is not working very well. Well, I'll give it one more shot. But what I'm going to be able to do is I'm going to make sure I hit mode here. Alright, so I hit mode, and I make sure I'm in degree mode. Alright, so that's what I would do. And if I quit back out to the home screen, I'm going to hit cosine, alright, cosine button right there, and 135. And I could close those parentheses if I want to. And if I hit enter, I get negative 0.7071067812. I just said cosine of 135 is negative root 2 over 2. So let's actually calculate that. Negative second square root of 2, get out of that under radical, divided by 2, and there we go. Those are the same thing. So your calculator is actually able to give you these ratios, but if you're clever, you can often find these out yourself. Not too shabby. And it's all about figuring out what quadrant you land in and what the reference angle is at that location.
Is that a good enough answer?
And, well, this is an exact answer. Whereas the calculator technically gave me a rounded to like 8 decimal places or 10 decimal places answer, where I have the exact answer here. Mostly because it happened to land on one of my special locations there. All right, so let's try another one of these here, and then I'll show you the trick. So let's find what sine, evaluate maybe, what the sine of, let's say, 240 degrees is. So I'm going to want to find two things. I want to figure out what is the value of sine, positive, negative, what's the polarity of sine in this quadrant, and what is the reference angle of 240. So 240 is like here-ish. It's past the 45-degree mark on that quadrant, if you're wondering. So let's see, for quadrant 3, what is sine's polarity in quadrant 3? What is sine's sine? It is negative because sine is the y value, and that is below the x-axis, so sine is negative, right? Is what I'm expecting. Actually, I could even think about this as this quadrant is negative for both points, x and y in that case. And what is the reference angle in this case? I'm going to subtract 180 from 240 to find the reference angle. So So alpha is going to equal 240 minus 180, which is equal to 60. So that means sine of 240 is going to equal the negative sine of 60 degrees. And what is sine of 60 degrees? I believe it's root 3 over 2. If we look that up. Yep. And that's how we can calculate these things, right? So, and I figured that out by knowing the polarity of my trig function in that quadrant and by figuring out its reference angle. Now, question. Looking back up at our polarity things. If cosine theta equals x and these are its signs, right, in those quadrants, what do you think would be true for secant theta, the reciprocal of x? Well, 1 over x. So for instance, if x was like -2 or something or whatever, the reciprocal of -2 is -1/2. It would keep the same sign. Does that make sense, right? Just flipping a number is not going to change its polarity. So it turns out that this is also true for secant. All right, so this is also true for secant. Maybe I could write a little note. So that's also true for that, which is equal to the 1 over x, right? And the reciprocal of sine, cosecant, is also going to have the same polarity as sines in those quadrants. Right, so cosecant theta equals the 1 over y. And maybe it's worth asking about tangents. Actually, we might be able to build one connection here. Let's talk about tangent for a second. All right, we said a moment ago that tan theta is equal to y over x, right? We also said that sine theta is equal to y. And we also said that cosine theta is equal to x. So using substitution, I could say that tan theta is equal to sine theta over cosine theta. Right? If I replace y with sine theta and x with cosine theta, and it turns out that's true. So if I want to figure out the signs of tan theta in its quadrants for tangent and actually cotangent, right? Tan theta is y over x, cotangent theta is x over y. All I have to do is compare the signs of sine and cosine and divide them. All right, so let's watch this. Check this out. So in quadrant 1, sine was positive and cosine was positive. What's a positive divided by a positive? Still positive. So tangent and cotangent are going to be positive in quadrant 1. For quadrant 2, sine was positive and cosine was negative. So dividing them would give me a negative. All right, so for these signs here, for tangent and cotangent, when sine and cosine agree, they're going to be positive, and when sine and cosine disagree, they're going to be negative, right? So for instance, quadrant 3, sine and cosine are both negative, and a negative divided by a negative is positive. And for the fourth quadrant, sine is negative, cosine is positive, so they disagree, so that's what we would get. Good stuff, good stuff. Now, let me teach you a trick for our chart that we made earlier. All right. Let's make our same chart. Sine, theta, cosine, theta, tan, theta. And this time I'm going to include 0, 30, 45, 60, and 90 this time. All right. So these are the angles that we have to have memorized in order to figure this out, right? So these are my thetas. I guess I could even label that column theta. Now it turns out, this is the trick. I'm going to draw a gross picture of a hand here. All right, so sine, let's see, here we go. Let me draw a hand. So here's a thumb, and here's 4 fingers. That's a sad looking hand. All right, I'm going to label these fingers. Here is the 0-degree finger. Here's the 30-degree finger, 45-degree finger, 60-degree finger, and the 90-degree finger. Okay? If I want to figure out what, say, sine of 30 degrees is, all right, let's say I'm considering sine of 30 degrees. What I would do is I will put down my 30-degree finger. All right, so you can imagine that that finger is now pointing down, right? Okay, I'm making like a weird turkey hand shape thing. I don't know. And the sine of 30, or actually the sine of any angle, is going to equal the number of fingers to the left of the downed finger divided by 2, or the square root of the number of fingers to the left, sorry. So here we go. So sine of 30, or sine of any angle, I'll give you the rules. Sine of theta is equal to the square root of number fingers to left, and then divide by 2. All right, so sine of 30, how many fingers are to the left of the down finger? There is 1 finger. So what's the square root of 1? 1, and divide by 2. Okay? The rule for cosine is similar. That's just going to equal the square root of the number of fingers to the right. And divide by 2. All right, so cosine of 30 degrees is going to equal, how many fingers are to the right? 3. So that's going to be the square root of 3 divided by 2. Now, real tricky, perhaps. What if I want to know tangent of theta? Well, a moment ago, I said that tan theta is equal to sine over cosine. So I could find the value of sine and then the value of cosine and then divide them. But what I want to point out is that if I divide both of these by 2 to get tangent, the 2's would just cancel out. The divide by 2 is no longer important. Yeah, so it's just the number of fingers of the square root of the number of fingers to the left over the square root of the number of fingers to the right. So let's see if we can make this chart. And then if I want to find the value of, say, like cosecant, I would just take whatever I get for sine and reciprocate it. All right, so I don't necessarily think we need to have those memorized because those ones you just flip them, right? So here we go. So sine of 30 I already said was 1/2. Cosine of 30 we already said was the square root of 3 over 2. Let's see if I can get my hand trick working here with the camera. All right, so here's my awesome hand. My tungsten carbide wedding ring. Bam, focus on that. Bam, good. All right, so if I want to say find, what are we at? We're looking at the sine of 0. All right, let's see if this makes any sense. Put down the 0-degree finger, that's my thumb. How many fingers are to the left of my thumb? 0. All right. I'm glad that's the case. I'm not a mutant. What is the square root of 0? Right, so the square root of 0 is 0, and divide by 2. What's 0 divided by 2? 0. So sine of 0 degrees is 0. Now, I just want to point out that that also makes sense over here, tying it back all the way to this. If I have a point right here, and I told you that the y-coordinate is equal to sine, how high up is this point? 0 units. So at 0 degrees, the y-coordinate is 0. So, let's figure out cosine of 0. How many fingers are to the right of my downed 0 finger? 1, 2, 3, 4. 4 fingers. So the square root of 4 is 2 over 2, and what's 2 divided by 2? 1. And notice that also would agree with this concept. If I plot that point and cosine is the x-coordinate, that point is 1, 0, and I just got 1 for cosine and 0 for sine, and that's exactly what I got. Okay? So it's a good little trick, and it seems to work with even these weird angles. Well, I had square root of 4 over 2, and the square root of 4 was 2, and 2 divided by 2 was 2. I mean, nope, 1. So if I want to find tangent of 0, well, number of fingers to the left is 0, square root of 0 is 0, square root of 4 is 2, 0 over 2 is 0. So tan of 0 is also 0. All right, let's try tan of 30. Put down the 30 finger. Right, we already found square root of 1 over 2 was 1/2 for sine. We already found that the square root of 3 over 2 was the value of cosine at 30 degrees. The value of tangent will just be the square root of 1 divided by the square root of 3, which is 1 over the square root of 3, which is root 3 over 3, which is what we found earlier. Okay, so that seems to work out. Now watch for 45 degrees. I think I'm only going to partially fill out this table and have you guys do the rest. 45 degrees. Put down the 45 degree finger. To find sine, it's the square root of the number of fingers to the left. That's 2. Root 2 over 2. Find cosine, square root of the number of fingers to the right. Root 2 over 2. So they're the same for 45 degrees because they're the same number of fingers on both sides. We also viewed that from the perspective of special right triangles of 45, 45, 90. The opposite and adjacent were both the same length. And that's why those are both the same value at 45 degrees. Root 2 over 2, root 2 over 2. Comparing that to the unit circle, what that's saying is a 45 degree angle, all right, if this was exactly 45 degrees, that's saying that this x and y coordinate are the same value, which makes sense. It's the same far over as it is up for a 45 degree, right? And it's saying that that value is root 2 over 2, or 0.707 over and 0.707 up. And that makes sense, okay? It makes sense. And let's lastly do tangent for this one. Actually, I might do tangent for one more after this. So let's see. So tangent for this, square root of 2 divided by the square root of 2 is 1. Let's see if you guys can analyze for me what happens for tangent at 90 degrees. All right. So let's go to the hand. Tell me, hand, how long will I live? I don't know. Doesn't matter. Square root of, let's see. Here's my 90 degree finger, right? Find tangent. Square root of 4 is 2 divided by the square root of 0 fingers is 0. 2 divided by 0? 2 divided by 0? It's undefined. Because we can never divide by 0. So it actually can never, ever happen. All right? And just to point out, sine at 90 degrees was 1. Cosine at 90 degrees was 0. 1 divided by 0 was undefined. And I guess I'll just fill out the rest of this. This one's going to be root 3 over 2. This one's going to be 1/2. And tangent at 60 degrees is going to be the square root of 3, which is what we found earlier. So you can actually use that stuff to answer other questions, which is all good stuff, good stuff, good stuff. Man, Still got one more concept to teach you. How do I fit all this in one lesson? All right. Now, I just want to quickly talk about trig functions of any angle in standard position. Which is what Colin asked a moment ago. Of an angle in standard position. Bam. Didn't quite fit it all in one line. That's close enough. So if we think about angles in standard position, right? Let's say this is what my angle looks like. And let's say this is the angle that I'm talking about. All right, so here's angle theta. Now, Colin asked, well, what happens if it isn't 1? All right, or something to that effect. You were asking, why are we using 1 and not some other number? Let's suppose that's the case and that I'm going out r units. All right, so let's say I'm going to a point here that's r units away. So some unknown radius, if I was trying to think about this as a unit circle. Then I could actually find, so if this point is x and this is y for the location of that point, I could draw my little triangle off of that if I wanted to still, and it'd be a right triangle. The overness would be x, the rise would be y. And I just want to point out that if I wanted to find r, you actually could, if I knew the coordinates of x and y. The radius is always going to equal the square root of x squared plus y squared, which makes sense. I don't know if you see where that's coming from. That's just Pythagorean theorem one step later. That's the same as if I wrote this a moment ago, right? X squared plus y squared equals r squared. It's Pythagorean theorem is all that's coming from. So if I gave you the coordinates of a point and wanted you to find the trig ratios for it, you could first find the value of r just by doing the square root of x squared plus y squared. And then you could find each of those trig ratios. Let's see, we're so used to writing these down now. Sine, cosine, tangent. And their reciprocals, right? Sine theta is going to be y over r. So instead of y over 1, it's just y over r. Cosine theta is going to be x over r. And tan theta is still going to be y over x. And we'll write down the reciprocals just for funsies. Why not? So that would be cosecant theta would be r over y. Secant theta equals r over x. And cotangent theta is equal to x over y. All right, so all sorts of stuff going on. I realize I've been pulling all sorts of ideas between angles in standard position, unit circles, our trig ratios. All of this stuff is colliding. Lots of stuff going on. I'm going to end this video here, though, for sake of time. But you've got all of the skills you need. It's just a matter of merging them together, and we should be good. So thanks, everybody. Have a great day.